There's a lot of talk about agents in 2025, but something I think is underappreciated is the usefulness of adding memory to LLMs, and something I've underappreciated too. So this is a video on how you can add read-only memory, which allows you to improve reasoning performance and also achieve effectively longer context lengths. Now, this is based on the MEM-GPT paper, which came out just over a year ago. It's an operating system. It draws an analogy between language models and the memory management of computers. Actually, I was at AI Engineer Summit in New York, and I saw one of the authors of that paper, Charles, give a nice presentation for his company, Letta, which is implementing much of this paper in practice. Now, why give LLMs memory? First of all, you might want to remember conversations from the past. And when I say past, I mean beyond the context length of your language model. Second of all, you might want to inject preferences for the model. You might be familiar in ChatGPT. It will know some things about you. If you ask ChatGPT, tell me a bit about myself or what's interesting about me, it will give you some answers. And that's because ChatGPT stores these little snippets of information throughout your history. And those snippets are injected within a block that's sent into the language model so that ChatGPT knows a little bit about you. And this allows you to personalize the experience. Third of all, you might want memory so you can read documents. You might notice if you use Cursor that it will read through files and it will paginate through them about 100 lines at a time. And what's happening there is those lines are being injected within a context block, and the model is then reasoning about those before moving to the next context block. That's an example of kind of read-write memory, something that I'll cover in a second video. So in this video, I'm going to explain broadly how memory management works. I'll explain the types of memory, read-only versus read-write memory, and why you would use both and what you would use each for. I'll talk about storing conversation history versus storing documents or other information. And I'm going to walk through building an agent using read-only memory. So at a high level, you can think of two big blocks of memory: local memory, which is the context of the language model, and then disk memory, which is your database, where you can store documents or the entire conversation history. And you can have reading and writing between these two processes. So you can have the LLM provide in its response a command to write to the database, and then you can provide also a command, have the LLM provide a command in its response to read or fetch based on a search of this database here. So here's my architecture. By the way, it is a little bit different than MEM-GPT. I'll try to explain my design choices. Not to say it's better, just to say there are some trade-offs, and I'll try to expose those. If this seems overwhelming, I'm going to describe it piece by piece, so be happy with just understanding at a high level here. I've got my local memory, I've got my disk and database. And for now, my database serves two purposes. It allows me to store the entire conversation history, the turns between user and assistant, and it also allows me to store documents. Now, these could be literal documents like PDFs, but in principle, this could also just be strings of text that the LLM decides to write to the database. There's no real reason to have these separate. They can be part of the same database, but it will just help. It'll just be helpful for us to separate this in terms of thinking of the conversation history, which is determined solely by the chat, and then this more flexible type of memory here, where the LLM could write bespoke strings to. That's why I've got the separation. Orange means read plus write, whereas red means read only. So the LLM is only able to read this. It's not able to write bespoke strings to the conversation history, because obviously the history is what it is. On the local memory side, you can see a few blocks that are being defined, and each block represents an allocation of tokens. We've got a system message, maybe 500 tokens here. Then there's a block here for read-only retrieval. So we can have the LLM issue a command to retrieve a conversation. It will then be entered into this block, or a command to read from the document database, which will also be written in here. Then there's a read-write block. Now, why is this read-write? Because this can be written by the LLM response. So this block allows the LLM to actually write to its local memory. So when I say read-write, I mean it's read-write from the standpoint of the LLM response. That's why the conversation history is read-only, because the LLM response cannot write to this, whereas it can write here and it can write here. And then there's the recent chat history. Now, although this is kind of a small block, it's actually going to be the majority of the tokens. It will constitute as many turns as we can fit within the context length. So the way we'll choose how many recent turns to include is by saying, okay, the local memory, in total, we've got, let's say, 4,000 tokens. We've got 500, 500, 500, and 500 allocated. So that's 2,000. Therefore, we've got 2,000 left for the recent chat history, and we will take as many prior turns as possible and include them that make up no more than 2,000 tokens and include them in the recent chat history. Everything else, in fact, all conversation history will be stored off of the local memory on the disk database and can only be retrieved if the LLM issues a command. So let me describe briefly how this works in a different way. We will store the most recent conversations. We will kick out the oldest conversations based on context management. And this is called FIFO or FIFO, first in, first out, which means any message that goes in will move towards the back of the queue and eventually get kicked out when we hit the context limit. Meanwhile, the whole conversation history is being written to the database, and it can be queried by the LLM if the LLM provides a command. I'll describe how that works later. But the LLM can say, okay, find me all conversations about giraffes. And then a series of turns that have giraffes in them will be written into this read-only memory, which will then appear within the context and will be readable by the LLM here. Again, just a reminder that when I say read-only, it's read-only from the standpoint of the LLM because it cannot directly write to this memory. It can only make a search and then allow for the conversations that are found to be written. The document database and queries work similarly. We have, let's say, an array of documents or a database of documents. The LLM can decide to query these documents again for something like noodles, and then the relevant documents would be written into this read-only memory from the standpoint of the LLM, so it's available in context. Now, for the read-write memory, what this does is allows the LLM to directly write into its local memory. And this is also designed to be first in, first out. So as it writes more and more, the older stuff will just get kicked out. Now, there are alternative management approaches where you can allow the LLM to, you can basically notify it that, okay, your local memory is getting full. You should rewrite your local memory into a summarized form. That's another approach that's taken in MemGPT. But maybe a slightly simpler approach is just to make it first in, first out, so that only the most recent content stays in there. Now, the reason for having read-write memory is you can allow the LLM to maintain in local memory important information. For example, if it's creating a document, it might want to store the latest draft of that document that it's writing within its read-write memory. It would not easily be able to do that if it is forced to write to the database, because once it writes to the database, it then has to execute a search, and that search may be imperfect and it may be difficult to consistently have that always being passed back to the read-only memory. So by providing a direct channel for the LLM to control what's in its context in local memory, we can allow it to kind of guarantee that information is available. So yeah, as I mentioned, I'm repeating myself here, but local read-write memory is needed to read long documents in chunks, because you're going to have a chunk that appears in the read-only memory. Then you'll want the LLM to probably store some of its notes on what it's read before the next page of the document comes in, and then it will store more of its notes here. Read-write is also useful for recording sentiment, as I mentioned with ChatGPT. It can basically say, oh, I'm talking to the user here who's called John or Mary, and just note here the user's name is John. John likes very short responses, so there's a direct pathway here to store that. Now, all of this about read-write memory I'm going to cover in the next video. For now, I'm going to focus just on the read-only memory and focus on retrieving from the conversation history. So we'll cover saving the conversation turns to database, kicking out old conversations from the recent chat history, and then seamlessly making queries to the LLM about past responses. Before I show you the implementation, I have two other notes I just want to say about pagination and database setup. So there's this beautiful idea called pagination. It's not a new idea at all, but it involves allowing a search to happen where you have search results that will have multiple pages. And when I say page, I just loosely mean page. I don't literally mean a document page. A page could be, say, 3 conversation turns. It could be 10 conversation turns. The key point is that you have a limited number of results and you can paginate through them by moving to the next pages. So here you might have the LLM call retrieve for a search string, say giraffes, and we find some results. There are 2 results on this page. And we also tell the LLM this is page 1 of 6. But now the LLM is able to retrieve the query from, retrieve the second page of results by passing in page 2 and see more results here. And this is basically just like Google search. Now, this idea, I think, is underappreciated. Many of you will be familiar with RAG, or Retrieval Augmented Generation, where we just search for the top K results, like the top most relevant 6 results. And the problem is if you miss the best result within those 6, you just get inaccuracy. But if you have pagination, it does take multiple steps, but in principle, the LLM is always able to get to the result it needs because it's able to just keep looking at the next page of results. And if you allow pagination, while it does add extra steps, it makes your search much more robust. In fact, you can now use simpler search methods. You may not even need embeddings to the same extent. You might be able to get away with simple keyword search, because even if your search method doesn't precisely find what you need, you're always able to just paginate. So I'm a big fan of pagination. This is something that is in the MemGPT paper as well. And I think it's probably underappreciated in the design of LLM operating systems. So we'll see how it works very nicely, paginating through prior conversations based on search. A few other notes here on database setup and retrieval. Actually, I'll do this in reverse. For this video, I'm just going to store the conversation history in JSON format. If you want to implement this in production, you should use Postgres. I have got a folder explaining how to do that using BM25 search, which is a pretty good, accurate form of search, including indexing for speed. There's a library called VectorCord. I'll probably do a bespoke video on this, but the files are within the advanced inference repo if you have access to that. If you don't, you can check it out. It's a paid repo available on trellis.com/advanced-inference. It's also the repo I'm using for this video here on memory. Just one other comment here. I haven't answered the question of how does the LLM make queries. So I've just loosely said, well, the LLM is able to write here, or the LLM is able to retrieve from the document database or retrieve from the conversation history. And the question is how? How are you able to do that? And the answer is there are a few options. One option is to do function calling. So you can have functions or tool calls that will involve reading from the conversation history, which will be a search. You can have functions that will read from the document database. You can have a function that will write to the memory. And this is definitely an approach you can use. In fact, in some ways, it might be a very good approach because language models now, for example, Claude, are quite heavily trained on function calling. And so their performance in multi-turns with function calling can be quite strong. So this is an advantage to function calling. A disadvantage to function calling is, first of all, it can be somewhat verbose. You might need to write quite a bit, inject quite a bit of content into the context to set up the function calling. But second of all, with function calling, it's less straightforward to allow the LLM to provide an answer and then decide what to do. Let me explain that a different way. If we just allow the LLM to use tags in order to fetch a memory, what we can do is have the LLM say, oh, let me think about that for a bit because we talked about giraffes, but let me see what prior conversations involve giraffes. And then it will write fetch memory giraffes, close tag fetch memory. So this is a fairly simple way to implement memory search just by providing XML tags, and then you use regular expressions in order to extract those tags. The easiest way to explain this is just for me to show an example, but I want you to appreciate that you could use function calling here. The pros are that it may just perform well because language models are now trained a lot for doing tool calls, but on the other hand, it can be a bit more verbose and a bit less flexible if you want answers to contain both text and what are effectively function calls, but done via XML tags. So that rounds out the presentation portion. And for the next portion, I'm going to work out of the repo, the advanced inference repo. It's present here at trellis.com advanced inference. It is a paid repo and you can purchase annual access to it on trellis.com. If you're not in a position to buy it, hopefully I'll give you enough high-level information here so that you could rebuild what I'm doing using Cursor and some of the guidance I go through. So with that, let's head over to advanced inference and let me increase my screen size a little bit. This repo has now got quite a lot of content. You can see on the left-hand side, there are folders, so it's organized by folders. There is a folder here now for vector code BM25 if you want a Postgres implementation of how to create a database for this. I'm just going to use a JSON file to keep things simple for now. There are many other scripts which you can find out more about on the web page I just showed, but the one we're going to look at is memory. And the README we're going to look at is right here. And we have our memory chatbot. Now, anytime I'm building scripts lately, I start off by creating a task.md file, and I use that to have language models help me to build the code base. So it's actually going to be helpful for me to just walk you through this task.md file and the different design features I describe. So this is something I've written out, also with the help of an LLM, but I have provided much of the guidance. And then I'll go through some of the key snippets within the code. I won't go through everything, and I'll show you how the chatbot works. In fact, maybe just to start things off, I'll show you the final product of what we're going to get so you can know what we're building towards. It's a simple chatbot where I'm able to access conversation history. So if you want to run this for the first time, you would do uvvenv to set up a virtual environment, pip install uv first, which is much faster than just using pip for everything, then uv pip install -r, and then requirements.txt. I've already installed all of those, and then uv run main.py to run the app here. So here we'll have a memory chatbot. You can exit by typing exit quit or buy, and the chatbot is called Jimmy. How are you, Jimmy? So I just say howdy to Jimmy, and the responses are going to be streamed here. So let's just say something simple here. I'm a big fan of pandas. They seem friendly, but are they really? And you can see I'm getting responses that are being streamed. And the key thing is when I build up a long conversation history, and I'll show later on one of the longer conversations, I'm then able to ask a question where it will go back and find out about something in the past. Actually, to do that, let's take a look at a longer conversation I have here about giraffes, incidentally. And I've built up a long enough history so that I'm longer than the context length I've set, which is fairly short. I've set a context length for the model of just 2,500 tokens. It's just for illustrative purposes. I would recommend actually setting this to 32,000. I think that's about the length, maybe 16,000, probably 32. That's about the length where the language models are pretty strong at reasoning. If you set it up around 100,000, I think you'll see some drop off in reasoning capabilities. So somewhere there is probably optimal. Now, while I'm at it, you can see the limits I've put for the local memory. This is my local read-only memory. I've allowed 1,500 characters. For user messages, I've limited to 250. For responses, 250. And when I make a query, or when the language model makes a query to get results, I'm limiting it to 3 results per page. So it will find 3 conversation turns in the history, and it will include those within my read-only memory. And if the language model, if the assistant wants to see more pages, it can do so, and it can paginate through them in groups of 3. So what I'm going to do is delete that short conversation I showed you. I'll just exit here. And I'm going to rename my saved conversation history just conversation history. So it now becomes the history that will be used for this chat. So when I rerun main now, even though this is a new conversation, it's actually a continued conversation where I have all of the prior conversation history available in the database. And actually in the UI, it will just load the number of conversation turns that are able to fit in the context window. So if I ask here, I can say something like, what was I saying about giraffes? And Jimmy's going to respond and say, let me check my memory about our giraffe conversations. And yeah, Jimmy is fetching from memory. It's doing a search for giraffe and giraffes. I'll explain why it does that a bit later. It's searching the memory, which really just means that the memories or the conversation turns are being written to the read-only memory. Then there's a message that goes to the language model saying the conversation history was added. And now Jimmy is generating a response and saying, okay, based on our conversations, you mentioned it's hard to keep giraffes as pets indoors. I was thinking about getting a pet giraffe because I had a big hole in my roof, and I thought that would be perfect for accommodating a giraffe. And Jimmy responded with some practical considerations. And now Jimmy says, I see there are more results available about our giraffe discussions. Would you like me to check the next page? And this is because Jimmy is seeing in the context that there are multiple pages. So it's now Jimmy's deciding to paginate. So I'll say, sure. And now Jimmy says, let me check the next page of results. So Jimmy's now fetching the next page by using these tags for fetch memory page. And now the memory is being updated to include page 2 of the results. So now Jimmy's looking at the next page of discussions and says, well, just moments ago you stated, I've decided I'm keen to have a pet giraffe. The whole solves the problem. So it's Jimmy's pulling up the second page. There's only 2 pages of results in this case, by the way, and adding on some reasoning based on what I said in those results. So you can see here, there are a few things happening. Jimmy is able to retrieve memories, and Jimmy is further able to paginate through memories, and actually is being prompted to check with the user as to whether Jimmy should paginate or not. Now you can try and make the pagination automatic, which can be a nice feature. Then again, it can lead to runaway, where the model gets into a loop, which of course you can stop as well via code. But the way I've done it for now is just to say that Jimmy should basically look at the first page and then offer to the user to look at a second and further page if those are present. So this is an illustration of how the conversation works. To make that even more concrete, let me show you the prompts. So within the code, I've allowed the prompts to be saved. And this is pretty helpful because it's going to allow us to see exactly what's being passed into the language model. So here, let me just make some room. This is the first query that I've made to the language model. So the query is, what was I saying about giraffes? And let's just look at how the full prompt is set up. So first we have a system message. You are Jimmy, a personal assistant with access to memory. You have 2 types of memory: local memory that contains recent conversation with the user. You can access this directly in the conversation context. So I'm explaining how basically the context is the local memory. The most recent memory messages are already included in your context window, so you don't need to search for them. And then there's disk memory. This contains your entire conversation history with the user. Memory contains 14 user message and 14 assistant responses from these dates. So you can see I'm dynamically injecting information about what conversations are stored on disk so that Jimmy knows that there are messages on disk and also a rough date range around those. Now, I've only had conversations today, so the date range is just today. Next, I explained when to use memory search. Only search when the user explicitly asks about past conversations or topics that aren't in the recent context. Do not search for basic questions like how are you? Do not search when responding to the current conversation topic. So these aspects here, that's me tuning the prompt because the model isn't following what I wanted when I didn't provide those instructions. So you don't want the model to search if the answer is literally in the past conversation turn, which is already in the memory. Now, I explained how memory works. So my guidance here is to be very transparent with the model on what is being done and how you're architecturing it. I'm saying when you search memory, the results are added to your read-only memory section in your system message. New memory results are appended at the end of your read-only memory. So I'm explaining exactly how they're appended. This read-only memory persists across conversation turns until replaced by new search results. Memory is managed on a first in, first out basis. And when new memory results exceed the token limit, the oldest memories are removed first. So this helps Jimmy to understand that there will be context loss when that overflows, and to react accordingly. So now I'm explaining how to search memory using fetch memory tags. And I'm being even more specific in saying that when including a search string, it should be a specific search query, including plurals, synonyms, and tenses. Now, if you're using BM25, you probably don't need to do this. You can just do a search query string. But because I'm doing a simple keyword search, if Jimmy searches for giraffe, it's not actually going to find the word giraffes. It will lowercase, so it will be case insensitive, but it won't include plurals. So you have a choice. Either you can get Jimmy to be more verbose and to provide all of the options here, like plurals and synonyms and tenses, or you can go for a more complex search algorithm like BM25, or like using embeddings, or a hybrid search with embeddings in BM25, which actually would give you the best results. So for example, if the user asks, what did we discuss about dogs last week? You would use, let me see if I remember, ... fetch memory, dogs last week, and then close tag fetch memory. Then I explain the results be added to read-only memory, and you'll see a confirmation message. So you remember in the discussion back here, when Jimmy does a search, there's this there's this confirmation message saying that the conversation has been added. Some search tips here. I explained that the search is simple keyword-based, case insensitive, and I explain how exactly to search. Next, I have pagination. So I explained that to paginate, you use fetch memory, then the page number here, X, and then close fetch memory. And notice here how I recommend, let me see. Yeah, I recommend when you see, to see more results, use this. Always inform the user that more results are available. So I'm basically saying, if you see that there's more than one page, you should let the user know that there's more available, so they might decide to see more. And here I explain that when fetching a new page, it replaces the previous page. So this is again a design choice. You could also do first in, first out, but what I'm deciding is I'm only showing one page from a given search at a time within that local read-only memory. I also emphasize that when this page gets replaced, that information will be gone. So the language model must summarize the key points from each page before moving on to the next page. And you could make this a bit better by saying the key relevant points, but I would have to do that in the system prompt, not here, because this is just a saved prompt. Then I provide an example. So I've got an example here. What have we discussed? Jimmy, let me check my memory. Here's the search string. After receiving the results, Jimmy says these things here and says, oh, there's more results available. Do you want to see more results? I say, yes, please check the next one. Then Jimmy checks the next page. And then after receiving it, provides more information here. So yeah, always try and provide examples. And yeah, then I close things off. Be concise in your responses. Unless asked to elaborate, your name is Jimmy. And I'm still in the system message here. So it is quite a long system message, but this is fine. Strong models like Claude Sonnet 3.7 will support this. And it's important and useful to give the examples as I did. So next we're seeing after the system message, the conversation turns. And notice that we will only include the most recent conversation turns, not the entire conversation turns, because they won't all fit within context. So effectively what you're seeing here is a list of conversation turns that do fit. And there are quite a few. I've allowed a context of 2,500 tokens. So you can see here, it looks like we have roughly about 4 or 5 turns. And that pretty much rounds it out. The last question I ask here is, what was I saying about giraffes? Then we just have some statistics that I've printed. So there are about 2,000 total tokens. Remaining tokens is the max response length. So effectively this query is going to be 2,420 tokens, which is under the 2,500 that we're allowing. So this was my first request. What was I saying about giraffes? That resulted in a call to memory. Now, when there was a call to memory, which we can check here, let's see exactly where it calls memory. So what was I saying about giraffes? The assistant responds, let me check my memory about giraffes, fetch memory, giraffes. And then there's the confirmation that the conversation history has been added. And indeed, it has been added. and it's been added to the memory, which is contained at the very end of the system message. So previously the system message just described the system message, but now you'll see if you scroll down to the bottom, there's a new section called read-only local memory. And here we include those results. And you can see it will say when we have retrieved the memory, it will say what the query was, it will say how many matching conversation turns, and then which page we're on. So already Jimmy knows there are now 2 pages. And the first page shows 3 memory results. So I had 3 conversation turns talking about giraffes. And it also says to see more results, use fetch memory page 2. So this is also helping the model to know how to fetch the next set of results. And indeed, that's what the model does. So if we scroll down to the very end of the next turn, you'll see the assistant has now said, based on our previous conversations, here what you said about giraffes. I see there are more results available about our giraffe discussions. Would you like me to check the next page? To which I say sure. And that results in another search of memory. So you'll notice now if we go to the bottom of the system message, which is right here, we're now seeing the memory search results for page 2 of 2. And you can see here the 4th message. And there's now actually a 5th message because that request in itself, the previous one, also mentions giraffes. So it's been included too. Now, if you really wanted, you could exclude this if you thought that it was throwing the model off. I don't think it is. So it's fine as is. But basically, we've gone back to see the second page, and now that second page is included in results, and that gives more information back to Jimmy. So Jimmy here is checking the results. And if we ran the next round of running the prompt, it would save the latest prompt that is being passed into the language model, and it would now contain Jimmy's response, which is looking at the next page of draft discussions. I see some updates here. So this is an explicit run through of what's contained in the prompt at every stage. It's specifically the prompt. That's why we don't see the response. When I save the prompt, I'm literally just saving what goes into the language model. But it gives you a very clear sense of the information we're sending in at each step and also of how the memory is managed. Okay, now that I've walked through the chatbot, it should be a lot easier to understand how I build the app, or at least how I describe now how to build it. So let's go back to the task.md file and I'll describe the key features. We have a minimalist chatbot client that manages local in-context memory and a conversation history on disk database. So I'll describe the local memory management, the disk database memory, how to retrieve conversations, some notes on what the client should do, like how you interact on the command line, some build notes. So actually do that. Use UV to install dependencies instead of pip, keep a README updated, include clear installation instructions in the README, create a requirements file with pinned dependencies. Do not include unit tests, do not use Alembic. Actually, this is wrong because I'm using JSON now, so this technically should be removed. No need to create a logging system. Do not create backup scripts. Try to keep the entire app to a minimum of files and keep the design simple and elegant. So those are my build notes. A few other notes for token counting, use 4 characters per token. Actually, Claude decided to use some other tokenizer, which is fine, but it can add a bit of slowness. And some notes on the license. Typically, the license will default to being MIT, which can be a problem if it's not public open source software. Just a few quick notes then on future improvements. As I described earlier, you can use Postgres with vector core BM25. You could also add embeddings. You could allow the assistant to search by date, not just by query string. You could add rate limiting and throttling. You could also add authentication and multi-user support. Okay, so let's now look at, I'm kind of working backwards here. Client, this is very simple. I'm just using a command line interface. You could also build a web app, and Claude would be well able to do that. But it's nice to use the command line interface just because it's easier for me to demo here and then show you some of the printed out contents. So for local memory management, I'm going to have a context length C defaulting to 4K tokens. Actually, I use 2K tokens in the demo just to make it even shorter. So I can hit the context limit and show you the history retrieval. The system message must always be sent as the first message. Allow up to LRM tokens for local read-only memory, so 1500 local read-only memory tokens. The user message is you defaulting to 250, response is or defaulting to 250, and then only include the most recent messages from the conversation history and local memory. This means no more than C minus U minus or minus LRM minus S, where S is the length of the system message. So this is how the context is managed. It's basically saying you've got enough room for recent conversations as the total context minus the allocations for the system memory, the local read-only memory, the user message, and the response message. Moving to the disk database memory, store the entire conversation history in a JSON file. Each user and assistant should be saved separately with metadata for time and date. So it's definitely very useful to include the date with each conversation, because now you're telling the model when that conversation was had. That's particularly useful. Also do the same with the system message, and calculation store for each reuse the token count of each turn. So token counting is important for context management. You don't ideally want to do that multiple times, especially if you're using a tokenizer. So we just store the token counts within the database, so they're available then when we need to assemble conversations on the fly. And the last section to look at here is the conversation history retrieval. The model may call its memory at any time by enclosing a search string with fetch memory tags. They're fetched via keyword search. Some do something a bit better than plain keyword. So it's not just a pure string match, it's actually splitting the string up into words and checking if any of those words are present in the conversation history. Find the closest default 3 turns of conversation, including timestamps. Indicate the total number of results and the total pages of results. This is telling the language model how many pages there are, that's important. Allow the model to request a specific page using fetch memory page tags. And the system message must track the current search query to properly fetch additional pages. So there are probably different ways to paginate, but the way that I'm doing is the language model searches, and then it can paginate through that given search. You could alternatively allow it to do a query where it specifies the query and the page at the same time. But I just felt this was the most straightforward way of designing it, where you have a query. Once those results come back, only then is it able to paginate. The local read-only memory should be managed on a first-in, first-out basis, with all the results being kicked out, such that the total number of tokens in the local memory never exceeds the local read-only memory, LRM. So this is just managing that local read-only memory block. I'm just doing first-in, first-out, and kicking out the older results. Next, for chat initialization, the very first time we'll say, hello, I'm Jimmy. But then when it reloads, we will show the most recent messages. And in the initial task, I said up to the 5 turns, but actually that really should be the amount of messages that fit in the context window. So I'm using the same approach for showing in the UI as I'm using for managing the context that I send to the language model. The UI should be consistent with how messages are displayed during an active conversation. Don't really think that helps much. Next, for response handling, use Anthropic's Claude 3.7 Sonnet latest via Light LLM. With Light LLM, you need to put in Anthropic right before the model name like this. Load the API key from an env file, include a sample.env, includes clear instructions on setting up the env file in the README. Add a stop token to the generation call. So when the language model calls to fetch a memory, it's going to include the closing tag, but then because we include that as a stop token, that token gets suppressed. So we actually need to add it back in again if we want to have it displaying consistently. So when a response is received, we check for a fetch memory tag that's not followed by a fetch memory tag, a close fetch memory tag, because it's been suppressed when we use it as a stop token. And this indicates the model wishes to fetch a memory. If it does wish to fetch a memory, apply a closing fetch memory tag, then use regular expression to extract the string after fetch memory tag and before the closing fetch memory tag. Perform the keyword search, store the search query for potential future page requests. Depending on the outcome, the following string should also be appended. So if the memory was added successfully, we indicate to the model it was added. If it failed to be added, we indicate that it failed, or provide a more descriptive error. And once the memory has been retrieved or is a failure, the LLM is called again with the assistant's response pre-filled with the original response and this updated information. So the assistant will say, oh, let me check my memory, fetch memory tag, search string, close fetch memory tag. Then that gets parsed, in which case there'll be a search. And if the search works, all of what I just said will have this confirmation appended to it. And then that will all be sent back to the language model, which will then essentially continue that assisted response, but making use of the information in it. For page requests, use fetch memory page. The system should use the stored current search query to fetch the requested page. So we're kind of caching the search so that we can page through it. And if no current search query exists, inform the assistant that no active search query is available. The response should be streamed, and the portions of the response should appear as they become available during the fetching process. So that's our response handling. Then we have the system message management. It's a personal assistant called Jimmy. The message should explain how memory works, and high-level information on the state of the disk or database should be included. So fairly simple description there, mostly because we've described everything above. And that pretty much brings us to the end of the task. So you can see all the steps here I have for putting together this assistant. And that's implemented then. Now I did need to go through iterations because I had to fix bugs. So if you just run this task.md file, you won't get exactly the same app that I have. I'll just take you through some of the key parts of the code. This is the main file here. It will make sure we have an Anthropic API key set in the environment variables. It will provide a welcome. So it's setting up a simple client. And then it will start the chatbot. And the chatbot will then start to loop. And this function is available within the chatbot file. So if I go to the chatbot file, and if I go right to the bottom, I'll find chat.loop. And you can see if it's the first run, we'll do a check here to make sure that we include this one-off message. And if it's not the first run, we'll continue on from the previous conversation. Now, when we run the conversation, we're going to get the displayable conversation history. This is a function in the memory manager that is just getting the conversation history that fits in the context. So that's how many turns we're showing. We're only showing how many turns are able to fit within that window. So then we display the previous conversation if it's not a new conversation, and then we start looping through the chat. Note that here we have the function, or we have the setup so that if the user types exit, quit, or buy, it will end, and it will end this entire chat. And otherwise, while it's true, we're just going to continue recursively calling generate response, which will run the generate response function that's ultimately running the chatbot. So here we have the generate response function. It's going to add a user message, adds the user input, then it gets the conversation context using the memory manager, and then it will save the prompt to file so that I was able to show you and inspect the prompt as I did earlier, make a call to the LLM to get the response. It will then check if there's a memory query. If there is a memory query, it will extract the string and perform the search. If it performs the search, then it's going to add that in to the local read-only memory right here. And then it will append this string to say that the conversation history has been added, or there was some issue with adding that. Then it's going to save the prompt to file if that's the case. Now, the other check we need to do is to see if there's a request for page requests. If there's a request to see a next page, then we're going to grab the page number and we're going to get the content of that next page of results and update the short-term memory, or rather the read-only memory. So here you can see we're removing the previous search results and then we're adding in the new page of search results. Then we pop on a message. Pop is a bad word to use there because that usually means remove. We add on a message here to confirm that we've gotten the next page of results. And then we are going to go back and get another response from the language model. So this is basically the loop. We have the user message. The user message goes to the LLM. We get a response. We decide if we're going to do a search or if we need to paginate. And based on taking those actions, we then send the updated messages back to the language model to continue until we get back a response where there's no request for a search or there's no request for doing a pagination. So this is the overall architecture of how the chatbot works. Let me see if I'll go through the memory management just to show you one or two of the key functions here. The memory manager has got a few features: conversation history, local read-only memory, system message. It does have an encoder here. So even though I told it just to use 4 characters per token, it decided to use the tokenizer for Claude anyway, which is fine. And then an ability to track the current search query. There are functions here for loading conversation history, saving the history, counting the tokens, setting the system message, adding the user message, adding the assistant message, getting the conversation context, and performing the search on the memory. And I will just go quickly through this search memory function because it's one of the key ones. We have add to read-only memory. That's adding content into the read-only memory, formatting the memory results, extracting the memory query. So these are the regular expression extractions for the memory query and also for the pagination query. A check to see if there's any more pages, which we can do if there's more than one page. Getting the statistics on the memory so we can pass that to the system message, and displaying the conversation history. This is the function I mentioned earlier. This gets the number of turns that fit within the context window. So very briefly, the last thing I'll do is go through that search memory function. So you can see here, it will take in a query and it will take in a page. So that's the page number. It's going to take that query, convert it to lowercase and split it into multiple words. And then it's just going to find any messages that has at least one of those words. So this is why it's important to prompt the language model to include plurals, to include past tense, if we're just using a simple keyword search. Once it decides that it's found messages that match that, it groups the conversation into turns. So what I do is I always provide conversation turns. That's user and assistant message. You could decide just to provide raw chunks, but I think it's much better if you format the turns of the history into these, format them into clean turns. It just structures the information a lot better than having these random equal sized chunks that we typically would do in a naive type RAG system. So yeah, I do a search, I find the relevant past turns, and then I have them grouped when they go into the context. So once they're grouped, I get the user message. Well, this is how I do the grouping. I find the corresponding assistant message, and then I calculate the pagination. The way I do that is by fetching how many turns I allow per page. I've defined that as 3 in the config. So this is how I define the pages. So if there are 4 conversation turns found, that means there's going to be 2 pages because there'd be 3 on the first and 1 on the second. And then finally, I can return the page results, the total results and the total pages here. And so this rounds up my overview of how to build read-only memory for a large language model. And it allows you to have these chats where your assistant is able to remember things from the past. In a future video, I'll extend this to include read-write memory, where the language model can directly write to its own memory. And this will allow us to do things like reading long documents in chunks, recording sentiments or preferences of the user, and will add an additional level of complexity, but also an additional level of power to what you can do with these LLMs that have memory. As per usual, the scripts are available on trellis.com, this time for advanced-inference. And if you have any questions, or you have special requests on things I should cover in more detail in the next video on memory, let me know below in the comments. Cheers.